Hello, and thank you for watching this video about FlowEFD version for Siemens NX. This video will briefly show how to set up and run a 3D CFD analysis on a CAD geometry. So we'll start by opening up the geometry that we want to analyze. In this case, we have a shell and tube heat exchanger now ready to move on to the 3D CFD analysis phase. I'll go ahead and launch FlowEFD. See right away it's going to add a FlowEFD toolbar to the ribbon at the top, as well as a flow analysis menu at the very top of the NX interface. So the first thing to do would be to check the geometry to make sure it's suitable to run a 3D CFD analysis on. You can either access this from the toolbar, or it also exists within the menu. We'll go ahead and include all the parts, select an internal flow type, and then we'll check it. And we can see that this check failed, and we're given a message that it's not a watertight model. It's fairly clear to see in this example that our gaps are coming at the inlets and the outlets. But if for some reason it weren't as easy to detect, FlowEFD does have a leak tracking tool that will allow us to find where these gaps are. And I'll use the leak tracking tool. I'll choose a face that I want on the outside of the fluid domain, as well as a face on the inside. And I'll find the connection. And there's a bright red line that shows me how the two faces would be in contact if submerged within a fluid domain. Now we need to close up these gaps. If we're more comfortable within the CAD tool, we can switch back to modeling and simply draw an extrude over the gap. And I'll go ahead and make that circle slightly bigger than the port itself, because FlowEFD doesn't have any problem with overlapping geometry. Now, if I don't prefer to use the CAD tool, FlowEFD also has a method by which you can quickly close these gaps. Switching back into FlowEFD, we can find a Create Lids tool that's going to allow me to find planar faces that I want to seal off. And so with a couple quick clicks, those faces are sealed off, and now I have a closed geometry. I can verify this by once again running the Check Geometry tool, and we can see that this time it was successful, and it was able to find a fluid as well as a solid volume within the domain. And to verify, there is a Show Fluid Volume feature that will allow me to check to make sure that FlowEFD is picking up the fluid volume that I intend to analyze. So now with our geometry set up for an internal flow analysis, I can go ahead and start a project. Once again, go into the toolbar. I'll click on the wizard button. I'll give this project a name that I can easily reference later. So I'll start with SI being my base unit, but I'll go ahead and change a couple things in here. We'll change our pressure to pounds per square inch, and I also want to change my volumetric flow rate to US gallons per minute. I do want to run an internal analysis type, and I want to include heat conduction within the solids as I transfer heat from a hot fluid to a cold fluid. Now I'll go ahead and pick those fluids. One of them I'll use water, and then the other one I'll pick this glycol-water combination. Glycol-water is not a part of the default database, but to add any fluid or solid for that matter, I can go into my engineering database, either through this wizard or, once again, there's a shortcut on the toolbar, and I can go ahead and add a new liquid. I can either give its properties in a static form, or more likely I'll have those properties in terms of temperature. And so I can enter a table of temperature versus that parameter. And you could see that you could do the same for conductivity as well as specific heat. Since I already have my fluid designed, I'll go ahead and cancel out of this without saving the changes, and I'll pick that fluid. Another key technology here is that Flow EFD will automatically detect whether the fluid is in a laminar or turbulent regime without having to go ahead and define the specific flow regimes. I'll go ahead now and pick a default solid material. I could adjust my wall conditions to have some sort of thermal interaction with that external environment if I wanted to, but for this case, I'll assume that outermost layer is well insulated. And then I can define my initial conditions here. Although while I'm thinking about it, I want to go ahead and go back to my unit set, and I want to change my default temperature to Celsius. Now we can skip back to our initial conditions. And moving on to the last stage, this is where I will define my mesh resolution. Lower on the slider bar means coarse mesh, fast simulation. Higher on the slider bar means finer mesh. We can see right away that a computational domain is defined. And if I go to my Flow EFD tab, I can edit that definition either by manually changing coordinates, or I can drag on any one of the faces to extend or shrink that fluid domain. I'll reset back to what Flow EFD detected, and I'll go ahead and hide that. Next, I'll go ahead and assign a fluid subdomain. From the project wizard, I could have defined one of these as my primary and then one as a secondary, but since I had both checked off, I'm going to need to go ahead and define both fluid domains. So the first one I'll define is for the shell, and I'll do that by picking one of those internal faces to detect that fluid domain. And then I'll have this one be water. This will be my cooling side. And if I wanted to make that abundantly clear, I could rename that domain. And then I'll go ahead and do the same thing for the tube side. Get rid of my previously selected face, and now capture the new face, and have that one be my glycol water mixture. I did define all the default solid materials to be that aluminum alloy to capture the heat transfer between the two fluids. However, this is also going to apply that aluminum material to those lids that I created as well. And in this case, I don't want any heat being transferred across those lids, so I'll set those as insulator materials. And we can go under our glasses and minerals to find insulator. Now I want to apply some fluid boundary conditions. We'll start with the hot side. And so I'll once again choose that inside face again. Apply an inlet volume flow rate, and we'll call this one 5 gallons per minute. Now I also want to apply a thermodynamic parameter so that this is our hot fluid side. So I'll go ahead and assign this a temperature of 210 Fahrenheit. And once again, just to clarify it, I'll rename that. And now I'll do the same thing for the cold side by changing which face I've selected. And this time we'll put in a 2 gallon per minute flow rate. And we'll leave our thermodynamic parameter as room temperature. Now we also want to apply downstream boundary conditions. And in this case, I'll just have the outlets of both domains be environment pressure. So now our geometry is set up for our CFD analysis. But before we actually run it, one other thing that we can do is to set up goals that we want to track, or items, parameters that we want to look at after the simulation is completed. So there's a couple different types of goals that we can apply. A global goal simply looks at the entire domain. So maybe I just want to keep track of the minimum and maximum temperature seen within either fluid. I can set a global goal for that. Surface goals that will allow me to keep track of things such as the heat transfer rate across the inside tube. And I'll go ahead and name that appropriately. Now I'm ready to run the simulation. So I'll return to the toolbar, select the Run option, and I'll let it both mesh and solve, although I could run those separately if I wanted. And here, FlowEFD pops up a window where it first meshes, and then it's going to solve the problem. And we can see we have a couple graphics here to visually show us what it's solving, as well as graphically show us. Of course, for the sake of the video, I'll go ahead and speed this up. So our simulation is complete, and we can now look at the results. First, I'm going to reopen FlowEFD to highlight some of the simulation times. We can see here to create a mesh of roughly 20,000 cells, it took FlowEFD's automatic mesher less than a minute. Once it created that mesh, it took just about a minute to complete the simulation. Of course, if you remember, we set our mesh resolution towards the lower setting, looking for a quicker simulation time. Had we set it to a higher level, we could generate more cells for a higher fidelity result. Now we'll go back into the model to take a look at some of the results. So first, we'll generate a cut plot of the temperatures. To do this, we'll select the data plane that we wish to display these results on. And then I'll go ahead and select temperature from the list of results. So the plot is created, but we can't see it because the geometry is in the way. FlowEFD has a button that we can push in order to hide the geometry and show us a cut plot. Another method that we can use to view results is to create a surface plot. And for this, we'll want to choose a part on which we can display the results. We'll go ahead and take a look at the heat transfer coefficient on the tube. I'll go ahead and change the boundaries just a bit. Another method we can use to look at results is a flow trajectory. And in this case, we can choose our boundary conditions to be the points of releasing said theoretical particles. I'll choose the shape that I want these trajectories to take on, and then let's go ahead and choose velocity. We can go ahead and animate this now to give it a sense of motion. We can also create a goal plot which will allow us to export those goals that we created into an Excel format. Another reporting feature we have is to actually create a Word document type report. I'll go ahead and choose from a template, which will print out everything I need to know about the simulation, including setup conditions, boundaries, and goals. Additionally, I can go ahead and add a screenshot to the report as well for a visualization. Thank you for watching this video.